Well, hello and welcome to this series of lectures on respiratory physiology. My name's John West, and I'm looking forward to discussing these interesting topics with you over the next few lectures. The material is based on lectures that we've given to the medical students at the University of California, San Diego over the last few years. And it also follows generally my book, Respiratory Physiology, The Essentials, although the lecture format allows us to expand on some material, particularly the topics that give trouble to the students. So where should we start? Well, I happen to believe that the function of the lung is best understood if we first look at its structure. And so this first lecture is going to be on the structure and function of the lung. And what part of the lung should we start with? Well, let's all agree that the primary function of the lung is gas exchange. The lung does other things too. It filters unwanted materials from the blood. It has metabolic functions, and it acts as a reservoir for blood. But by far its most important function is gas exchange, and therefore a good place to start would be at the blood-gas barrier where the diffusive gas exchange occurs. And in this nice drawing here, we can see the lung with the chest wall having been removed. The lung, we can see the right lung here, the left lung here, and between them is the mediastinum, which contains the heart. The air comes into the lung through the trachea, divides into right and left main bronchi, and the airways get smaller and smaller until we eventually get to the alveoli. The blood comes into the lung from the right ventricle through the pulmonary artery. Again, the blood vessels, the small pulmonary arteries, branch many times until we get to the capillaries in the alveolar walls. And it's in the alveolar walls that the blood-gas barrier exists and the gas exchange occurs. The lung is also supported within the chest, and as the diaphragm goes down and the rib cage enlarges, so the volume of the lung is increased, and this is how we take in a breath. Now, if we look in the depths of the lung, we see the alveoli with the capillaries. This is a nice light micrograph taken rapidly freezing the lung, so we believe that it shows the conditions during life. And you can see the alveolar spaces here, and in the alveolar wall, you can see the capillaries. And actually, you can see the individual red cells. And it's the blood-gas barrier which separates the blood here from the gas here, across which gas exchange occurs. Now, this blood-gas barrier is extremely thin, and in fact, we can't identify it in a light micrograph like this. So we need to go to an electron micrograph, and this is shown here. Now, what a beautiful picture this is. You might want to take a print of this and perhaps put it on your refrigerator door or your bedside table. It's just a beautiful electron micrograph, and actually we're going to come back to it from time to time. But let's have a look now and see what it shows us. Here's the capillary in the alveolar wall, which is running across the slide here, and we have alveolar gas on both sides of the capillary here. Within the capillary lumen, we can see the red blood cells and also the plasma. Now, the wall of the capillary is the blood-gas barrier. Blood on one side, gas on the other. And we can see here at the top the very, very thin blood-gas barrier. The thickness of this is only about 1/3 of a micron. Notice we have the scale down here. 1/3 of a micron, which is fantastically thin. Now, wait a moment. What do we mean by 1/3 of a micron? Well, a micron is a millionth of a meter or a thousandth of a millimeter. And a red blood cell, like we see here, is about 7 microns in diameter. A red blood cell is just clearly visible in the light microscope, and so when we go down to a micron or even less, as we see here, we're beyond the limits of resolution, and that's why we're using an electron micrograph here. Now let's look at the structure of the blood-gas barrier on this side. And you may notice, by the way, that this side of the barrier is much thinner than this side. In fact, the blood-gas barrier, the capillary, is polarized, so one side has a thinner barrier than the other. Let's look at the thin side first. The outermost layer is the alveolar epithelium, very, very thin cell, as you can see, and here is the nucleus of this, as it's called, type 1 alveolar epithelial cell. Then the innermost layer is the capillary endothelium. We can see it here, and here is the nucleus of the capillary endothelial cell in this beautiful electron micrograph. Between the two layers is the extracellular matrix, or if you like, the interstitium. And on the thin side here, the extracellular matrix is made up of the fusion of the basement membranes of the alveolar epithelium and the capillary endothelium. So the two cellular layers are here, and the fusement of their basement membranes makes up the interstitium. Now, one of the most important constituents of the interstitium is the type 4 collagen in the basement membranes, because we believe that's responsible for the strength of the blood-gas barrier. As you might expect, a barrier that is this thin is rather fragile, and if the pressure inside the capillary rises to abnormally high levels, you can get ultrastructural changes in the blood-gas barrier and leak fluid into the alveolar spaces. That situation is called stress failure. Now let's turn to the lower section here, the lower part of the slide, and you can see that the blood-gas barrier contains additional material. If you look closely, you can see the collagen fibrils in the blood-gas barrier here. Also, if we go over here, and this is a little bit more difficult to identify, but you can see actually a fibroblast, a cell with its prolongations going into the thick side of the blood-gas barrier. Now, this is such a beautiful electron micrograph that I am reluctant to spoil it with graffiti, but that's what we've done. On the next slide, we've just shown the structures, we've labeled the structures, and I've done this so that you can come back sometime if you wish and just refresh your memory on what the various structures are, because it's very important that we understand the structure of the blood-gas barrier. Now, we said that the barrier is extremely thin, 1/3 of a micron in many places. And why is that? Well, that brings us to the principles of diffusion, gas diffusion, through a tissue sheet. And this is shown on this slide. Now, we're going to come back to this slide in much more detail in a later lecture, but we should look just at some of the principles here. What this slide says is that if we have a tissue sheet, for example, something like a postage stamp, for example, then the volume of gas which moves across the tissue sheet here is proportional to the area of the sheet, proportional to a constant, which is called the diffusion constant, and the difference in partial pressure between one side of the sheet and the other. It's also inversely proportional to the thickness of the sheet. And so what this means is that we need as thin a sheet as possible and as large an area as possible. Well, now the blood-gas barrier in the lung, as we've seen, is phenomenally thin in much of its part here. It also has a very large area. In fact, the area of the blood-gas barrier in the human lung is about 50 to 100 square meters, enormous area. You may say, well, how is that prodigious area generated? Well, there are about 500 million alveoli, and in each of the walls of the alveoli, you've got these capillaries with their blood-gas barrier, and that is what allows us to have this barrier that has an enormous area and is extremely thin. Now, I like to think of the lung as a symmetrical organ, with the blood-gas barrier in the middle, air coming in from one side via ventilation, and blood coming into the other side via the pulmonary circulation. And we're going to look at these two systems, the airway system and the blood vessel system in turn, and let's start with the airways. And here we've got a gorgeous photograph of a cast of a human lung. This is made by taking a lung at post-mortem and injecting a polymer into the airways, allowing it to set, and then somebody has taken a fine set of scissors and cut off all the alveoli so that we end up seeing the small airways in the periphery. And as you can see, it's a very, very beautiful picture. The air comes down the trachea here during inspiration, and it meets a junction here, which is called the carina. Carina is Latin for keel. And the airways then divide, the trachea then divides into a right main bronchus, left main bronchus, then lobar bronchi and sublobar bronchi, and so on, all the way down to the alveoli. As we penetrate further and further into the lung, the airways become more numerous, they become narrower, shorter, and they eventually end up in the alveoli. So let's have a look at, first of all, the trachea. Here's the trachea, or the windpipe, it's sometimes called, and it's constructed of cartilaginous rings, as you can see. Here's a section here, and the cartilaginous rings prevent the trachea from collapsing when the pressure outside it is greatly increased, for example, during a cough. However, the posterior part of the trachea, shown here, is membranous in character, and there is some invagination when the pressure outside the trachea is increased. Now let's follow the airways down into the lung, and here's a very nice image. This shows an airway as we enter the lung. This is the airway here with all the cartilage in its wall, and it's accompanied by two blood vessels. One of them is a pulmonary artery, another is a vein. One is blue, the other is red. Which is which? Well, you were right if you said that the blue blood is in the pulmonary artery, because the lung is the only organ in the body where the incoming blood, the pulmonary arterial blood, is deoxygenated, whereas the blood leaving the lung is oxygenated. And that's why the pulmonary venous blood shown here is red, because the hemoglobin is oxygenated, and here in the pulmonary vein, in the pulmonary artery, it's blue. This image, incidentally, was made by freezing a lung so that the events were kept as like they were in life, and then sectioning it and giving us this very nice image here. Now we're further down into the lung. We can see the airway here, and we can see its branches going out. And here's another branch of the airway here. And we're beginning to see the alveoli in what we call the parenchyma of the lung. That's the region, the respiratory region of the lung where the alveoli are, called the parenchyma. Here we are somewhat further down, another beautiful slide. You can see the airway here and its accompanying pulmonary artery here with blue blood. And then over here, you can see a pulmonary vein. Now the artery is still accompanying the airway, but the vein has moved away to the edge of the lobule. And that will continue down to the respiratory portion. And now, of course, we can see the alveoli. They're larger than they were in the previous slide. We're going down further, and the magnification is increasing. Now, this is a more conventional thin section and shows an airway here at the bottom. You can see now that the cartilage has disappeared. There's some smooth muscle in the airway wall here. That's what we can see. And we can very clearly see the alveoli around the airway, and you notice how they're attached to the airway wall. We can also see the accompanying pulmonary artery with its smooth muscle in the wall. We can see the red blood cells, and this hole here is because of some shrinkage during preparation of the section. And you can see from here that you would expect the airway to be pulled open by the alveoli as the lung expanded. As the lung expands, the tension in the wall, in the alveolar walls increases, and this pulls on the airway and expands it, and the same is true of the blood vessels as well. Here we are further down the lung, and this is a very beautiful scanning electron micrograph showing a small airway here and the alveoli attached to the wall on the outside. And again, you can get this impression that the alveoli are going to be pulling the airway open. You'll notice that there are some holes, apparently, in the walls of the alveoli. These are called pores. They're probably closed during life because of fluid lining the alveoli. Now we're even further down the lung, and now we see a few alveoli budding off the airway walls. Now, as we'll see in a moment, there are a number of generations of airways before we see any alveoli at all. But now we get to what we call the respiratory bronchiole, where there are alveoli budding off the airway, and now, of course, these alveoli have a blood gas barrier, and they contribute to gas exchange. And as we go further down this small airway, we come to airways that have more and more alveoli branching off their walls, as you can see. So there are about 3 orders of respiratory bronchioles. Now we're even further down the lung. Here's an airway here, coming down here. And now we get these blindly ending alveolar sacs, as they're called. And in the ends of the sacs are the alveoli. And then finally, we see the alveoli. We saw this slide before, and we're going to see it again, incidentally. And this is the end of the airway system. And in the walls of the alveoli, we can see the capillaries and the blood gas barrier here. Now, let's take an imaginary walk down the airways and see what we can find. We'll see some interesting sights. Here's one. Here's a so-called goblet cell. This is in the airway wall, and you can see an opening through which mucus is discharged onto the airway wall. The airway has a mucociliary system, and this is very important in keeping the airway clean. There are cilia, and you can see examples here, and these cilia help to transport the mucus. And here's a good view of the mucociliary system here, and I partly show it to indicate that the goblet cell, which we saw in the last slide, is here in the airway epithelium, but actually more important from the point of view of providing mucus or seromucus material are the glands deep in the airway wall, shown here in a drawing. And you can see a duct takes the mucus up to the airway, and that's where the mucociliary escalator is located. And there are, the mucus is tenacious. If dust particles fall on it, they're swept up towards the epiglottis, where they're tipped over into the gastrointestinal tract. Here are some cilia, beautiful electron micrograph, scanning electron micrograph showing cilia. And also we can see another type of cell called a Clara cell. The function of the Clara cells is not fully understood, but they are believed to secrete another substance which contributes to the mucus lining layer. Here's a drawing which summarizes some of the cells in the epithelium of the airways as we go down from the large airways through the smaller airways, here called bronchioles, down to the alveoli. Initially, you see these tall columnar cells with cilia on top, and maybe the odd, that may be a Clara cell there, or possibly a goblet cell. Then, as we go further down, the height of the epithelial cells decreases, but they are still ciliated, until finally we get to the alveoli, where the cells are very flat, so-called squamous in character. And here's a type 1 epithelial cell here, and here's another type of epithelial cell here. So let's look at the cells in the alveoli. And the first one we should look at is the type 1 alveolar epithelial cell. Now, we saw this before, you remember, in the electron micrograph of the capillary, but here's another nice view. Some people think this cell looks a bit like a fried egg. It has a central nucleus here, like the yolk of the egg, but then spreading away from it are these very long protoplasmic extensions. The cell body spreads a long, long way away from the nucleus. As a matter of fact, when the electron microscope was first introduced and people got their first views of these cells, some anatomists thought that the type 1 alveolar epithelial cell didn't have a nucleus at all. They just couldn't find one. They're few and far between. But of course, they do all have a nucleus, but the protoplasmic extensions are very extensive. That's the type 1 cell. Now let's look at this one, which is, I should add actually, that the type 1 alveolar epithelial cell is the main cell for the structure of the alveoli. It provides the pavement, if you like, of the alveolar surface. Most of the alveolar surface is covered by the type 1 alveolar epithelial cell. It's a fairly lazy cell, doesn't undergo much in the way of metabolism, but it's very important from the structural point of view. Now let's compare that with another kind of alveolar epithelial cell. This is the type 2 alveolar epithelial cell. It's quite different, as you can see. First of all, its shape is quite different. It's got a sort of globular shape here. It's got a ring of microvilli, little sort of hair-like structures around it, like around the edge, a bit like the tonsure of a medieval monk. And you can see the holes through which it's secreting material onto the alveolar surface. Now this material is surfactant, or it's precursor of surfactant. And we're going to be hearing much more about surfactant later on. But just briefly, surfactant is a critically important material because it reduces the surface tension of the alveolar lining layer and therefore confers stability on these alveoli, which otherwise would be very unstable. So the type 2 alveolar epithelial cell is a highly metabolic cell. It's producing this surfactant, and it's quite different, as we can see, from the type 1 cells. Incidentally, we can see type 1 cells around them here. Another cell that we'll see in the alveolus is the alveolar macrophage. Here's another very beautiful scanning electron micrograph showing the alveolar macrophage here. It's a bit like an amoeba. It moves around the surface of the alveoli by amoeboid activity. It can phagocytose particles. It can engulf foreign particles. And its job is to keep the alveolar surface clean. The alveoli do not have the mucociliary escalator. That's limited to the airways. So another kind of mechanism is required to keep the alveoli clean, and this is the alveolar macrophage. This is a beautiful slide because we can see alongside it a type 2 alveolar epithelial cell with its holes and its microvilli, and then in the background here we have the type 1 alveolar epithelial cell, so that's a very lovely slide. This slide shows another alveolar macrophage, and initially you may find it a little bit difficult to work out what's happening. Let me show you. Here's the macrophage here with its nucleus here. And here's the wall of the alveolus running up here and running along here. And so what we've got is a macrophage lurking in the corner of an alveolus. And you'll notice that it contains some material. In fact, these are remnants of surfactant. Surfactant, as we'll hear later on, turns over quite rapidly within the lung, and it leaves remnants shown here, and these are picked up, swept up by the macrophages, engulfed. You can always recognize surfactant material because of its onion skin-like appearance. It's got a lot of layers, and that's what the macrophage is doing here. Now, let's go back a moment and look at our cast of the airways of the lung. As we said before, very beautiful, very elegant system, but what a complicated system. Suppose we wanted to try and work out the mode of gas flow in the lung, in some of the airways of the lung. How could we possibly cope with such a complicated structure as the one shown here? And a very important advance was made by a man called Dr. Weibel a few years ago. He's a Swiss anatomist, a friend of mine, And one day he sat down and he counted all the airways of the human lung. Not only did he count them, but he measured their caliber, their diameter, their lengths, branching angles, and so on. You know, the Swiss are very good at counting things, and he had the patience to do this, and he ended up with a system, a model of the lung, which admittedly is something of an oversimplification, but nevertheless is extremely valuable in understanding the airway system. And this is shown here. He said that if we consider the trachea as generation number one, this thing Z means generation here, then it divides into two daughter airways, the right and left main bronchi. And all the airways divide, as we say, dichotomously. You've got a parent airway, divides into two daughter airways. And that continues down through generations 2, 3, 4, and so on, to smaller and smaller airways. And on the average, he said, there's about 16 generations of branching before we see any alveoli at all. So this region of the lung is what is called the conducting zone. It doesn't take part in gas exchange. There are no alveoli, no blood-gas barrier. So this is simply the conducting zone, and it's often called the anatomic dead space, dead because there's no gas exchange within it. The volume of the anatomic dead space is about 150 ml. And then the last of these conducting airways is called the terminal bronchiole. Bronchiole meaning a small bronchus. Terminal bronchiole. And that subtends, or supplies, if you like, a unit of gas exchange, which is called an acinus. That's the unit of gas exchange. And you begin to see alveoli budding off the walls, and therefore these are called respiratory bronchioles. And on the average, there are about 3 generations of these. Then you come to airways where the whole of the wall is lined by alveoli. And these are called alveolar ducts, as you can see, probably about 3 generations of those. And finally, we get to the alveolar sacs, which are blindly ending, and these are covered with alveoli, and of course, that's where the blood-gas barrier is. Now, I said that the volume of the conducting airways, the anatomic dead space, is about 150 ml. The volume of the respiratory zone, which is where the alveoli are, is about 3 liters in the human lung. So the conducting volume is, of course, much less, but it's very important that we understand the difference between these two types, these two regions of the lung. And we're going to be talking much more about that in the next lecture when we talk about ventilation. So we've been talking about the airways. Now I want to switch and talk about the blood vessels. And here's a beautiful picture showing a cast of the airways on this side, this is the right lung here, and the cast of the blood vessels on this side here. And the blood vessels in this particular cast, the pulmonary artery is shown in red here. That's what he chose to use for the color of the pulmonary artery, and you can see the pulmonary veins in blue. And you can get a general feeling that the pulmonary blood vessels branch in roughly the same way as the airways do. Airways branch, as we've seen many, many times until you get to the alveoli, and is the same is true of the blood vessels. In fact, as I've said before, the small pulmonary arteries tend to run alongside the airways until we get down to the respiratory zone. Now, the next slide shows a small pulmonary artery on the left here, and alongside it is a systemic artery. That's an artery from the rest of the circulation, say from an arm or a leg or somewhere, and they have about the same caliber. Actually, this one is slightly smaller than this, but you'll notice that the walls are completely different. The small pulmonary artery here has rather thin walls, as you can see. This is cut diagonally here and makes it look a bit thicker, but they've got very thin walls, whereas the systemic artery has a very thick wall. A lot of smooth muscle here, small amount here. Why the difference? Because the pulmonary arterial system, the pulmonary vascular system, is a very low pressure system. The pressures in the pulmonary artery are only about an eighth or so of those in the large systemic arteries. And so there's a very big difference between the two. Now, as we go down, let's follow the arteries down, and here we come to an image that we've seen before, but we'll have another look at it. Now we can see a smaller pulmonary artery. We can see the smooth muscle in the wall here, red blood cells, of course, in the lumen, the alveoli around it here, and that has its accompanying bronchus here with smooth muscle in the wall. So the smaller pulmonary arteries have small amounts of smooth muscle, and actually it's rather patchy. We'll talk about that again later on. So there's nothing in the pulmonary arterial system which is like the systemic system, where the small arteries have lots of smooth muscle in the walls and they act as throttles. That's not the case in the pulmonary vascular system. And then we get down to the alveoli that we've seen now a couple of times before, the capillaries in the wall and the blood-gas barrier here. Now, if we look at the capillaries in the alveolar wall, face on as it were, and let's imagine that we're in an alveolus and we're looking at the wall of the alveolus, just as I'm in a room and I'm looking at the wall of the room. That's what we're looking at here. We're looking at the alveolar wall face on, and you can see that the capillaries form a very intricate network of capillary segments. And so some people object to calling these capillaries tubes or pipes. They think they form this very intricate network, and we can see that even better if we go to another type of lung. This is a frog lung, an amphibian. There's quite big differences between the lung of a frog and the lung of a mammal like a human, but nevertheless we've got a very good view of the capillary segment here. Here's the artery over here, the vein here, and you can see this very dense arrangement of the capillary network, so much so that some physiologists don't like to talk about flow in individual capillaries. They talk about a sheet flow. And an analogy is an underground parking garage where all the air in the garage would be blood, and you've got posts separating the two sides of the sheet of blood from time to time. So that's one way of looking at this. Now here's a drawing showing, and being a drawing, you shouldn't believe everything it says, but I think it makes a nice point, and that is it shows that towards the bottom, towards the alveoli here, you've got blood from the pulmonary artery shown in blue here. Notice that it's accompanying the small airway down here to the respiratory region. The blood probably traverses 2 or 3 or 4 alveoli between the end of the pulmonary artery, where it branches into the capillaries, and where it's picked up and taken away in a pulmonary vein. And again, what the artist has shown is the small pulmonary artery in the center of the acinus here, and the pulmonary vein running back along the outside, as we've seen before. Let's have a look at a small pulmonary vein, and that's shown here. Now, how do I know it's a vein? Well, the best way of knowing it is that it's not accompanied by an airway. It's actually very difficult to distinguish a small pulmonary vein from a small pulmonary artery. They both have very thin walls, as this one does. There's a very small amount of smooth muscle in the wall here. I can see a little bit here, very little. And you can see the red blood cells inside the pulmonary vein. And again, you can see how closely the alveoli are applied to the vein. And so it's not a surprise that as you expand the lung and you increase the tension in the alveolar walls, you tend to increase the caliber of the pulmonary veins as you do the arteries. One of the features of this micrograph is that we can see, not easily, but if you look carefully, you can see a potential perivascular space in the outside the vein here. That's important because it's really a potential space, a virtual space, if you like, under normal conditions. But if there is edema of the lung, in other words, if fluid comes out of the capillaries under some conditions, when you raise the capillary pressure, for example, it moves along and collects in these perivascular spaces around the small veins and around the arteries. And you get a cuff of fluid, as we'll see in a later lecture when we talk about pulmonary edema. So that's an important feature of these blood vessels. They have as it were, a sump, a perivascular region here, which can fill with fluid under certain conditions. Now, I've been talking about the pulmonary circulation, but I should emphasize that there is a second circulation of the lung. It's called the bronchial circulation, and it's very much smaller than the pulmonary circulation. Of course, the pulmonary circulation takes the whole of the cardiac output. The whole of the output of the right heart goes through the lung, just as the whole of the output of the left ventricle, the left heart, goes through the rest of the body. And these two circulations are in series. And again, we'll be talking about that in more detail in a later lecture. So the blood flow through the lung is very large. It's something like 5 liters a minute, an enormous amount of blood flow, which is necessary in order to oxygenate the blood. But there's also another circulation shown here. Here's a bronchial artery, not easy to see, bronchial artery coming off the aorta. Sometimes they come off the intercostal arteries. And these bronchial arteries supply the larger airways, the airways down to the respiratory portion of the lung. Of course, the respiratory zone doesn't need any bronchial circulation. It's got plenty of blood from the pulmonary circulation. But the larger airways do not see the pulmonary circulation, and therefore they need a small amount of blood from the bronchial arteries to nourish them. And we should bear in mind that there is a second circulation because it becomes important under some conditions. So let's summarize some of the most important points we've made. We started off by emphasizing that the primary function of the lung is gas exchange. And so that led us to look at the blood-gas barrier in the wall of the capillary, deep in the lung. We had a very beautiful electron micrograph showing that. And we saw that the thickness of the blood-gas barrier is fantastically thin, of the order of 0.2, 0.3 of a micron. We also saw that the capillary is what's sometimes called polarized, in the sense that it's very thin on one side, but it's thicker on the other. And the other side is where the fluid exchange occurs. We pointed out that the thin side of the blood-gas barrier is vulnerable because it is so thin, and it's the type 4 collagen in the basement membranes that apparently is responsible for the strength. We then looked at a very beautiful cast of the airways of the lung and saw this series of branching tubes, and we wondered how anybody could make sense of such a complicated structure. But it was very fortunate that the Swiss anatomist Weibel sat down one day, counted all the airways and measured their lengths and their branching angles and their sizes, and gave us a model of the lung which is very useful. One of the features of this model is that the anatomic dead space, the conducting airways, have a volume of about 150 mils. We then took an imaginary walk down the airways to see what we could see en route, and we found that the airways were lined with cilia and mucus, and we have a mucociliary escalator which removes deposited pollutants from the lung. We also saw some interesting cells, the goblet cells that produce some of the mucus. We couldn't see the seromucous glands, which are hidden in the airway wall, but their duct comes up into the airway. We saw the cilia, of course, and also the Clara cells, which apparently are responsible for secreting other materials onto the surface. Eventually, we got down to the alveoli, where we saw that there were 2 types of alveolar epithelial cells. The type 1 alveolar epithelial cell, which is a bit like a fried egg with a nucleus in the center and big protoplasmic extensions going out. And that's the main cell, the main pavement cell, the main structural cell of the alveolus. We also saw the type 2 alveolar epithelial cell, quite different. It's a globular cell, has microvilli, and we can see the holes in the cell often through which the material that reduces surface tension, so-called surfactant, is secreted. We also saw in the alveoli the alveolar macrophages, because the alveoli do not have the mucociliary escalator to clean them. Instead, they have these macrophages that roam around the alveoli and engulf foreign particles. We then took an imaginary swim down the blood vessels, and we saw that the pulmonary arterial system is a series of branching tubes, very like the airways. In fact, the arteries accompany the airways down to the gas exchanging area. We saw that the walls of the arteries are much thinner on the pulmonary circulation than the systemic circulation because the pressures are so much less. The capillaries form a very dense network of interconnected segments in the alveolar walls, so this is very efficient for gas exchange. We also noted that the small veins have a perivascular space, or perhaps a potential perivascular space, which we'll be talking about more when we come to edema, and the same thing is true of the arteries as well. And finally, we just mentioned briefly the bronchial circulation. It's a very, very small part. It's only a fraction of the pulmonary circulation, but it's important because it is responsible for the nutrition of the large airways down to the gas exchanging regions. So that's the end of our discussion of structure and function. And next time we'll move on and look at the topic of ventilation. Well, welcome back. In this session, we're going to look at the topic of ventilation, which is the process of getting the gas, the inspired gas, from the air to the alveoli so that gas exchange can occur. But before we do that, I thought it would be interesting to take a brief bird's eye view of the topics that we're going to look at in the subsequent sessions. And to do that, we'll start with this nice basic model, which shows the airways of the lung here, the alveolar gas compartment, the blood gas barrier, and the capillary blood on the other side. And what we're going to be looking at this morning is ventilation, which is the movement of gas to the alveoli. This will be followed by the topic of diffusion across the blood gas barrier, as shown here. Then we're going to look at blood flow, which is the process of moving the oxygenated blood out of the lung and allowing the CO2-laden blood to come in. Then we're going to look at gas exchange, which has to do with the matching of ventilation and blood flow. We're going to follow that with a look at blood gas transport as the oxygen is carried to the periphery of the body. And blood gas transport also deals with CO2, which has important effects on acid-base balance, so we're going to deal with that topic. Next, there'll be mechanics, which is the way the forces that support and move the lung. Then we'll look at the control of ventilation, because the oxygen and CO2 levels are measured in the arterial blood, and they're used to regulate the level of ventilation. Next, we'll look at defense systems, because the lung is always exposed to pollutants which are inspired, and we need to look at the way in which the lung keeps itself clean. And then we're going to look at the lung under stress, several stresses, one of which is exercise. And this is Dr. Roger Bannister breaking the first 4-minute mile barrier. And finally, we're going to look at the lung at the limit. And here we have Dr. Chris Pizzo taking alveolar gas samples on the summit of Mount Everest. So now let's turn to ventilation. And we've seen this beautiful cast of lung airways before. Very elegant, as you can see, but desperately complicated. And as we said before, how can we possibly understand what's happening in such a complicated system of airways? But fortunately, a Swiss anatomist, Dr. Weibel, sat down, as we mentioned before, one day and counted the airways in the lung and measured their sizes and so on. And he came up with an idealized model of the airways, which is to some extent an oversimplification, but nevertheless is a tremendously useful way of looking at the airways of the lung. And what he said was that there is, first of all, a conducting zone here, starting at the trachea and going all the way down to the terminal bronchioles, which are the last airways that don't contain alveoli. So all this is the dead space, the anatomic dead space, a volume about 150 mils. And then we get to the respiratory zone, or sometimes called the transitional and respiratory zone, which is where the alveolation starts. The respiratory bronchioles have a few alveoli, and then more and more occur until we get down to the alveolar sacs and the alveoli. And this is by far the largest volume of the lung, and of course is the volume concerned with gas exchange. So let's look now in more detail at some of the aspects of ventilation, and I'm going to start with one of the implications of the Weibull model, which is shown here. Now, what we've got here is the total cross-section of the airways of each generation, plotted against the airway generation itself, as you can see. And the way we get this information is, first of all, we take the trachea, and we measure the cross-sectional area, and we put that point there. And then we go to the right and left main bronchi, that's the next generation. We measure the combined cross-sectional area, and we put that point in, and so on. And as you can see, the result is that over the first few generations, the cross-sectional area, total cross-sectional area, doesn't change much at all until we get to the region of the respiratory zone. And there is an enormous increase in the cross-sectional area. It's a little bit like a trumpet, where you've got a long initial part and the flaring at the end of the trumpet. And this has very important implications for ventilation, for gas flow. It turns out that because of this enormous increase in cross-sectional area, the forward velocity of the gas, because of convection, becomes very small in this region of the lung. Now, what do I mean? What I'm saying is that each generation of airways has the same volume of gas going through it, of course, and that when you get to an area where a region where the cross-sectional area is very large, the forward velocity of the gas by convection becomes very small. By convection, I mean the normal flow of a gas or a liquid, like pouring beer out of a pitcher, for example, as an example of convection. So what happens when we get to this respiratory zone and the forward velocity of the gas through convection becomes extremely low? It turns out that another mechanism of gas transfer takes over, and this is diffusion. Diffusion in the gas phase is responsible for most of the movement of the gas in the respiratory zone. Diffusion means the random movement of molecules being bombarded by other molecules around them, and this is the way the gas moves from the predominant way in which it moves from the terminal bronchioles to the peripheral alveoli. Now, this has important implications in lung disease because it turns out that most of the pollutants therefore deposit in this junction here between the conducting zone and the respiratory zone. The reason is that pollutants are small particles, or aerosols as we call them, like tobacco smoke, for example. And what happens is that when the pollutants get to this region of the lung, the respiratory zone, their diffusion rate is extremely small. Although they're small particles, they're much more massive than the molecules of air. And for that reason, they're unable to traverse this region from the junction of the conducting zone and the respiratory zone to the peripheral alveoli. And a nice example of this is shown in this image here. Here we have the deposit of dust in a coal miner's lung. So a lung looked at autopsy, and you may not be able to recognize what's happening here. What we've got is a terminal bronchiole coming in. We've got the respiratory bronchioles here, and the edge of the acinus is around here. I can see it, but it's not easy for someone who's not familiar with these things to see it. And so the artist has put in a cartoon at the top to show us what's happening. And as you can see, the dust is found in the immediate vicinity of the terminal and respiratory bronchioles. The peripheral alveoli are completely spared of dust. And the reason for this, as I said before, is that the dust of the coal dust is sufficiently massive that it can't diffuse peripherally here, and so it deposits in this region. And that's very important because we believe that in bronchitis, inflammation of the airways, the first changes take place in these small airways here, and this is because of the deposition of the pollutants. Incidentally, I should just mention here as a caution that the fact that we find the dust here doesn't mean that it hasn't been transported to some extent from elsewhere, but nevertheless, we know this is the region where the dust is deposited. Well, now let's look at some of the volumes and flows in the lung. And again, we're going to start with our simple model with the conducting airways here, the alveolar gas, the blood-gas barrier, and the capillary here. And here we've added the ventilation and the blood flow, the ventilation coming in here and the blood flow coming in here. And as I mentioned earlier on, I like to think of the lung as a symmetrical structure with ventilation on one side of the blood-gas barrier and blood flow on the other. And here are some typical volumes of the lung. First of all, we've got the tidal volume. That's the volume of each breath. And that is approximately 500 ml. Now, of course, there's a good deal of variation around this, but that's a good ballpark figure, 500 ml for the tidal volume. But of course, not all of that tidal volume gets into the alveolar gas compartment. Some of it remains behind in the anatomic dead space. In fact, 150 ml does. But the volume of the alveolar gas, of course, is enormous. In this example, which another ballpark figure, about 3,000 mils, about 3 liters. So, as you might expect, the largest volume of gas in the lung is in the gas exchanging region. Now, when we go across the blood-gas barrier, we're in for a surprise because the volume of blood in the pulmonary capillaries is only about 70 ml. So there's a big disparity between the volume of gas in the lung undergoing gas exchange at any instant and the volume of blood. And that shouldn't actually surprise us all that much because you remember when we saw a cross-section of alveoli with their capillaries, what we saw was mostly gas. Here's the alveolar gas, here's the blood, and obviously the volume of the blood is very much less than the volume of the gas. And this has to do, incidentally, with the fact that diffusion rates in the gas phase are much faster than diffusion rates in the liquid phase here. Now, when we come to look at the volumes per unit time, or the ventilations, we see that the figures on the right here. Now, let's assume that the frequency of breathing is, say, 15 breaths per minute. Again, of course, another ballpark figure, but it's approximately the correct value. So if the tidal volume is 500 ml, the frequency is 15 breaths per minute, that means the total ventilation in this particular example is 7,500 mils per minute. But of course, not all of that gas gets to the gas exchanging regions of the lung. Some of it is left behind in the dead space. So the amount of fresh gas that gets to the gas exchanging regions per minute is going to be the tidal volume less the anatomic dead space, 500 less 150, 350 ml, times the frequency of 15, which gives us an alveolar ventilation in this example of 5250 mils per minute. This is by far the most important number on this scheme here because the alveolar ventilation is critically important. It's the amount of fresh gas getting to the alveoli per minute and a very important variable. Now, what about the amount of blood getting to the blood-gas barrier every minute? Well, of course, that's the cardiac output. The whole of the output of the right heart goes through the pulmonary artery to the pulmonary capillaries. And the cardiac output is of the order of 5,000 mils per minute, 5 or 6 liters a minute, something like this. So now we see an interesting thing. In spite of the disparity between the volumes of the alveolar gas and the capillary blood at any instant in time, the volumes reaching the blood-gas barrier per minute on the gas side and the blood side are approximately the same. In other words, the ratio of alveolar ventilation to pulmonary blood flow is about 1. And we're going to hear much more about the ventilation-perfusion ratio in due course. Okay, now let's talk a little bit about measuring the lung volumes with a spirometer, which is frequently done in the pulmonary function laboratory. A spirometer is simply an upturned bell, shown here, usually made of light metal, like aluminum, for example. It's immersed in water, as you can see, and there's a tube that connects the interior of the spirometer to the subject. As the subject breathes out, the spirometer goes up, the pen goes down. As the subject breathes in, the spirometer bell comes down, and the pen goes up. So here we have somebody breathing normally here. This is normal breathing, and these are the tidal volumes. It's the tidal volume here. And as we saw before, it's around about ½ liter. And then at this point, the subject is asked to take a full inspiration, go up as far as he can, increase the volume in the lung as far as he can, and the volume in the lung then is what's called the total lung capacity, as you can see. And then at this point, the subject is asked to breathe out as far as he can, and he breathes out all the way down to what we call the residual volume. In other words, he's not able to expel all the gas from his lung. There's always some left in the lung, even after a maximal expiration, and this is called the residual volume. And you could also see that the volume at the end of a normal expiration here is, of course, larger than the residual volume and is called the functional residual capacity. Okay? The volume that the subject breathes out with this maneuver from total inspiration to total expiration is called the vital capacity. So it's clear that we can measure several volumes with a spirometer. We can measure the tidal volume, for example, and we can measure the vital capacity, but we can't measure the residual volume, the functional residual capacity, or the total lung capacity because we can't measure the volume of gas in the lung at the end of a full expiration. Now, just for a little light relief, I want to show you a picture of John Hutchinson, who developed the spirometer in about 1850, something like this. And this is a picture from his original paper. And you can see this well-dressed gentleman breathing into a spirometer. And wouldn't it be nice if all of us dressed as nicely as John Hutchinson did? So going back then to the spirometer measurements, how are we going to measure these other volumes? We can't measure them with a spirometer. How are we going to measure the functional residual capacity? Because often we want to know that. And one way of doing that is what we call helium dilution. To do this, we take a spirometer and we put a relatively small concentration, say 5%, something like that, of helium in it. Now, why helium? Because helium is a very insoluble gas, so that when the subject breathes helium, almost none of it, essentially none of it, is taken up by the blood. So we start with a given concentration, C1 of helium in the spirometer. We know the volume of the spirometer, which we call V1, and the tap is closed at this point, and the subject is breathing through a valve box, and so he's not breathing from the spirometer. But then we open the tap, and he starts to breathe from the spirometer. And we allow him to do this until there's equilibration of the helium concentration between the spirometer and the alveolar gas. And he starts to do this at FRC, functional residual capacity. And we wait until the helium is equilibrated, evenly distributed. During that period, incidentally, we add oxygen to make up for the fact that he's consuming oxygen, and we also absorb the CO2 that he produces, so we keep the volume of the spirometer constant. And at the end of the equilibration period, we write a simple equation. We say that because no helium was lost, then the concentration times the volume that we started with here is going to be the concentration that we finish with times the initial volume, V1, plus the volume of the lung. And since he was turned in to the circuit when he was at the end of a normal expiration, that's functional residual capacity, we can easily derive the FRC from this equation. So that's a relatively simple measurement to do. It used to be used a great deal. It's not used quite so much now because we have a different method, another method of measuring these lung volumes, and I'm going to talk about it now. It's more complicated, at least to explain, but it's actually simpler for the subject to do. And that is the technique using a body box, or to give it a fancy name, the plethysmograph. The body box is simply a box, an airtight box, rather like an old telephone booth. And the subject sits inside that, and we measure the pressure inside the box with a sensitive manometer. Now, we're showing it here with a water manometer, but we don't use that. We use an electronic manometer because that gives us we need that kind of accuracy, sensitivity. And so what happens is as follows. The subject has his airway occluded. We turn a tap in the airway, and he tries to inspire against a closed airway. Now, of course, he can't get a lot of gas into his lung, but he can get some by rarefying the gas, and so there's a small increase in volume of the lung. As a result of this small increase in volume, the volume of gas in the box decreases, and therefore its pressure increases. Now, here we're using Boyle's law. I don't know how many of you remember Robert Boyle from about 1650, but Robert Boyle said that if you've got a volume of gas, pressure times volume is a constant at constant temperature. That's Boyle's law, and that's what we're using here. And so what we say for the box in this initial measurement, when the subject makes an inspiratory effort, is the initial pressure and volume, P1 V1, is equal to P2, which is the pressure after he made the inspiratory maneuver, times V1 minus delta V, the original volume, which has been reduced by the volume that the lung changed, the delta V. And from that, we, of course, can derive delta V. Now we apply Boyle's law to the gas in the lung, and we measure the pressure in the airway when the subject makes this attempted inspiration against a closed airway. And we start with a pressure P3, and he's at FRC when he makes this attempted inspiration. After he's made the attempted inspiration, we've got a pressure P4, and now the volume is the FRC plus delta V. Well, we know delta V from the original set of measurements, so we plug delta V into here. It's the only unknown, so we can calculate the FRC. Now, that's a little bit complicated, and I'm sure some of you will want to sit down later on and work through it yourself, because it maybe is a little bit complicated, but it's basically an application of Boyle's law to two situations. First, the gas in the plethysmograph, and secondly, the gas in the lung. This, incidentally, is a method that's used very extensively because although it looks rather complicated for us, for the subject it's very simple. The subject simply sits in the box and makes this respiratory maneuver. As a matter of fact, he doesn't just make an attempted inspiration, he pants against a closed airway, inspiration, expiration, attempted inspiration, expiration, and it's rather simple. And the device simply reads off the functional residual capacity, a very elegant device. Incidentally, it turns out sometimes that the measurements made by helium dilution and with the plethysmograph are different. Of course, in normal subjects, as you might expect, they're the same. But in some patients with lung disease, they're different. And the reason is that the plethysmograph measures the total volume of gas in the lung, whereas the helium dilution only measures the volume of gas which communicates with the mouth. And sometimes these are different in a patient with lung disease. Sometimes there are obstructed airways, and therefore the helium dilution gives a smaller volume than the plethysmograph does. So that's sometimes useful information in patients with lung disease. Okay, now let's turn to the measurement of ventilation. And first of all, we can think about measuring the total ventilation. Well, that's very easily done. We simply connect a subject to a valve box. A valve box is simply a device that separates the inspired and the expired gas, and we collect the expired gas over a given time, say 5 minutes or so, collect it in a big bag, then we measure the volume in the bag and we know the time that we've measured, and so we get the total ventilation in litres per minute. That's a relatively simple thing to do. But total ventilation is not a particularly useful measurement. What we really need to know is the alveolar ventilation, and that is more difficult to measure. And I'm going to tell you about two methods of measuring that now. The first method is to exploit the fact that the tidal volume here is made up of two sources. You've got the dead space gas, part of the expired gas here in the tidal volume comes from the dead space, and the other part comes from the alveoli. And so we can say that the total ventilation is equal to the dead space ventilation plus the alveolar ventilation. And let's show how we can do that using symbols. And now tighten your seatbelt, because you haven't seen these symbols before, and initially they may be rather daunting, but they're not really. So what we're showing here is the way we can measure alveolar ventilation by subtracting the dead space ventilation from the total ventilation. And what we're saying is that V, the volume, V stands for volume, sub T means tidal. So this is tidal volume, this is dead space volume, and this is the volume coming from the alveoli. And incidentally, as we go on, you'll see that in the gas phase, we also always use uppercase letters to indicate the gas phase here. We use lowercase for the blood phase, which we'll be talking about next time. So having set up this equation, the tidal volume is equal to the volume coming from the dead space plus the volume coming from the alveoli. We can multiply each term by the respiratory frequency, N, number of breaths per minute, and that gives us the fact that the Vt times N, which is the total ventilation, which we conventionally indicate as V dot E, E meaning expired, that's just a convention, V dot meaning volume per unit time. And those of you who can remember back at your calculus may remember that sometimes dV by dt, the volume per unit time, is indicated by a dot over the V. It's one of the conventions. So that's the convention we're using here. V dot E is volume per unit time. So that's the total ventilation is equal to the dead space ventilation, the ventilation of the dead space, plus the ventilation coming from the alveoli. Well, we simply rearrange that, and that gives us the alveolar ventilation, an equation for alveolar ventilation. Now, you may say that looks like a very simple thing to do, and it is, except that it's not so easy to measure the volume of the dead space. The volume of the dead space actually doesn't change all that much, and you can predict it reasonably well sometimes, but even so, it's somewhat messy to assume that. And we have another method of measuring alveolar ventilation, which is extremely important, although a little bit complicated at first. And let me introduce it this way. This shows the same diagram as we had before, but it makes a slightly different point. The point it makes is that all of the CO2 in the expired gas comes from the alveolar compartment. Okay? As we said before, the volume of the tidal volume, the expired tidal volume, comes both from the dead space and from the alveolar compartment. But, of course, the dead space doesn't contain any CO2. You may say, why? Well, because the dead space contains the inspired gas from the previous breath left behind in the dead space. There are no alveoli in the dead space, no gas exchange. Indeed, that's why it's called dead. And so there's no CO2 here. So all the CO2 in the expired alveolar gas comes from the alveolar compartment. And that allows us to set up an equation, again, tighten your seatbelt a bit, allows us to set up an equation here. And what we're saying is all the expired CO2 comes from the alveolar gas. So the volume of CO2 per minute exhaled, V dot CO2, volume per unit time, is equal to the alveolar ventilation times the percentage concentration of CO2 in the expired gas. In other words, if you've got 5% CO2, only 5% of the molecules of CO2 are coming from the alveolar gas. So what you can do then is instead of using a percentage concentration of CO2, we can use what's called the fractional concentration. Now, all the percentage concentrations add up to 100, the fractional concentrations add up to 1. And so if we've got, say, 5% CO2, the fractional concentration is 5 over 100 or 0.05. So all the fractional concentrations add up to 1, percentage ones add up to 100. And therefore, we can write the equation that the CO2 produced is equal to the alveolar ventilation times the fractional concentration of CO2. Okay? Now, it turns out, and here I have to go ahead a bit because we haven't covered this yet. We're going to cover it in the next lecture. The partial pressure of CO2, and you'll have to just take it from me for the moment. The partial pressure of CO2 is equal to the fractional concentration times a constant. In other words, the partial pressure is proportional to the fractional concentration. And we don't need to worry too much about this constant K. But this allows us to put in, instead of fractional concentration, we insert PCO2, or PCO2 over K for fractional concentration, and that gives us the final equation, which is called the alveolar ventilation equation. It's desperately important. We're going to be using it extensively in the following lectures. And what it says is that the alveolar ventilation is equal to the CO2 production divided by the PCO2. Now here we're showing it as the PCO2 in the alveolar gas. But it turns out that in normal subjects, the PCO2 of the arterial blood is the same as the alveolar gas. And believe it or not, it's not all that difficult to measure the PCO2 in arterial blood. It's done all the time. So this turns out to be a very important equation in the subsequent work we're going to be doing on gas exchange. You can see, for example, that if the CO2 production is normal, which it generally is, then the alveolar ventilation and the PCO2 are inversely related. In other words, if we double the alveolar ventilation, the PCO2 is halved. If we halve the alveolar ventilation, the PCO2 is doubled. And this alveolar ventilation equation, as it's called, is an extremely important equation, and we're going to be using it extensively in our later work. So let me now summarize what we've been talking about up to date. We're going to just be talking to look over the important points. First of all, we looked again at the complex geometry of the airways in the lung. We had a cast of the airways, and we despaired of being able to say much about it, but fortunately Dr. Weibel came along and he gave us a model of the airways, a bit of an oversimplification, an idealized model, but extremely valuable. And one of the things that it showed us is that the cross-sectional area of each generation of airways increases greatly as we go towards the alveoli. And the upshot of that is that the forward velocity of the gas becomes so low in the periphery of the lung that diffusion is the most important mode of gas transfer. That explains why pollutants are deposited in the small airways. And that's very important in understanding the pathophysiology of diseases such as chronic bronchitis. We then looked at the various volumes of the lung, and we pointed out that although the dead space, the anatomic dead space, is extremely important, it's only about 5% of the total volume of lung. We also saw that the volume of gas in the alveoli is very large, about 3 liters typically, but the volume of blood in the pulmonary capillaries at any instant is extremely small, only about 70 mils. However, in spite of the great disparity between the volumes of gas in the alveoli and in the volume of blood in the capillaries, the volumes per unit time of ventilation and blood flow are about the same, because the total alveolar ventilation in the example we showed was about 5 liters a minute. That's the same as the total blood flow, which is the cardiac output, about 5 liters a minute. So the ratio of ventilation to blood flow is normally about 1, and that's a ratio that we'll be talking about a lot when we come to consider pulmonary gas exchange. We then talked about the volumes of gas and how we measure them, and we showed that we can easily measure the tidal volume and the vital capacity with a spirometer. No problem there. However, we can't measure volumes such as the functional residual capacity or the residual volume, because the subject cannot breathe out, cannot expire all the gas in the lung. There's always some left at the end of a normal expiration. And so we have two ways of doing this. One is to use helium dilution, where the subject is connected to a spirometer that has helium in it, and he rebreathes, equilibrates the helium. Helium is essentially insoluble, and so we can calculate the volume of the lung from using that technique. The other technique was plethysmography, or using a body box, where the subject makes inspiratory efforts against a closed airway, and using Boyle's law, we're able to calculate the FRC. And that turns out to be a very important technique used in the pulmonary function laboratory. And finally, we talked about the measurements of ventilation, volumes per unit time. We pointed out that total ventilation is easy to measure. We just collect all the expired gas over a period of 5 minutes or so and measure its volume. Alveolar ventilation is more difficult to measure. One way is to subtract dead space ventilation from total ventilation. That gives us alveolar ventilation. But the problem there is that we don't know exactly what the dead space is, and therefore this is not an ideal way. And the best way by far is using the expired CO2. We're using the fact that all the CO2 and the expired gas comes from the alveolar compartment. And by working through those equations, we come up with the alveolar ventilation equation, which shows us that the alveolar ventilation, for example, is equal to the CO2 production divided by the PCO2, the partial pressure of CO2. There's a constant there as well, which we needn't bother about, and that equation becomes extremely important, as we'll see later on. So that's the end of our discussion of ventilation, and I look forward to seeing you next time. Welcome back. This session is devoted to the transport of oxygen and carbon dioxide by the blood, and it's often considered after pulmonary gas exchange because, in a sense, it's the next link in the movement of oxygen from the atmosphere to the mitochondria. But we're going to look at it now because in talking about diffusion and pulmonary gas exchange, we need to use concepts such as the oxygen dissociation curve, and so it makes a lot of sense to talk about them now. And I'm going to start by looking at some of the important concepts having to do with the gases, the concentrations, partial pressures, and so on. And here we have a sample of air, dry air, at sea level, and the concentration of oxygen is 21%. That means that of all the molecules, 21% of the molecules are oxygen molecules. So the concentration of oxygen in dry air is 21%. And we can also show that using this nomenclature here with the square brackets, concentration of oxygen. We can also refer to it as 21 ml per deciliter. Same thing. Now, percentage concentrations all add up to 100. But in some cases, it's more useful for us to use what are called fractional concentrations. And the only difference is that the fractional concentrations add up to 1. So the fractional concentration of oxygen then would be 0.21, and you can see that all the fractional concentrations, all the gases, would add up to 1. Now let's look at the notion of partial pressure. It's a very important idea. We use it extensively. And the partial pressure is simply the oxygen concentration, in this case the fractional concentration, multiplied by the barometric pressure, which at sea level is 760 millimeters of mercury. So we multiply 0.21 times 760, and that gives us a partial pressure of oxygen in dry gas of 160 millimeters of mercury. Now there's a minor complication that we should deal with here, and that is the effects of water vapor. Because when air is inspired into the lung, it is warmed and moistened and saturated with water vapor at the prevailing temperature of 37 degrees Celsius. And at that temperature, the partial pressure of water vapor is 47 millimeters of mercury. Now that only depends on temperature. It doesn't depend, for example, on barometric pressure. You go to the summit of Mount Everest where the barometric pressure is much less, but the partial pressure of water vapor at 37 degrees Celsius is still 47. That's very important. As a matter of fact, if you increase the temperature to 100 degrees Celsius, then the water vapor pressure is 760. And that is the reason why water boils at that temperature of 100 degrees Celsius. So in order to calculate the partial pressure of oxygen in moist inspired gas, we have to subtract the water vapor partial pressure, which is 47. We subtract that from 760. That gives us the partial pressure in the dry gas of 713, and therefore the partial pressure of oxygen is 0.21 times 713, which comes out to 150 millimeters of mercury. So that's the partial pressure that we're actually dealing with. The organism, if you like, is exposed to a partial pressure of 150 millimeters of mercury in the moist inspired gas. Now let's look a little bit further at the effects of dissolving the gases in liquids. And on the left here we have a cartoon showing air, moist inspired air at 37 degrees C, has a PO2, as we've seen, of 150 millimeters of mercury. And we allow that air to become equilibrated with water below it. By equilibration, we mean we wait until the number of oxygen molecules entering the water is the same as the number escaping. So we've got equilibrium. And the question is, what is the partial pressure of the oxygen in the water? The answer is that it's the partial pressure of the gas in equilibrium with the water. Now that might sound like a rather simple thing, a simple concept, but actually initially some students get confused about this. For example, they'll be faced with blood, arterial blood that has a PO2 of 100, and initially they might ask questions like, well, is that caused by the dissolved oxygen, or is it caused by the oxygen linked to hemoglobin? Not useful questions. The only way we can think of the partial pressure of a gas in a liquid is the partial pressure of the gas in equilibrium with the liquid. So that's a very important concept that we've talked about here. Now we saw that the concentration of oxygen in air is 21 mils per deciliter. What about the concentration of the oxygen in the liquid? Well, it's very much less. And that, of course, is because the solubility of oxygen in water is relatively low. In fact, the solubility is shown down here as 0.003 mils per deciliter per millimeter of mercury. And so the amount of oxygen at a PO2 of 150 is going to be 150 times 0.003, and that comes to 0.45 mils per deciliter. Okay, so that's oxygen in physical solution. Now you may say, well, why can't we use oxygen in physical solution in the body to provide the required amount of oxygen to the periphery? And a simple calculation will tell us that that's impossible. Let's look at it this way. The solubility of oxygen, we said, was 0.003 mils per deciliter per millimeter of mercury. PO2 in arterial blood, which we haven't really discussed yet, we will extensively eventually, but take it from me that it's about 100 millimeters of mercury. And therefore the oxygen dissolved in arterial blood is going to be 100 times 0.003, or 0.3 mils per deciliter, which is equal to 3 mils per litre. Now, suppose the cardiac output during heavy exercise is 30 litres per minute. That means that the maximum oxygen available is going to be 90 mils per minute. However, the tissues require about 3,000 mils per minute of oxygen, 3 litres per minute maximal oxygen uptake. So obviously the oxygen in solution is not sufficient. There's got to be another mechanism for oxygen transport. And of course, as we all know, this is hemoglobin. Just as a matter of light relief, there are animals that exist without oxygen-carrying pigments, and one of them is the Antarctic ice fish. The Antarctic ice fish has no hemoglobin. And you may say, well, how does it get on? Well, I suppose maybe it's a bit lazy, but the other thing is that it is at a very cold temperature where the solubility of oxygen is greatly increased. However, I wouldn't recommend this particular evolutionary solution. I think we've got a better one with our use of hemoglobin. Now, I'm not going to talk a lot about the structure of hemoglobin because it's really the province of the biochemists, and it's an extremely interesting subject, but let's just review it very briefly. Hemoglobin, the hemoglobin molecule, first of all, has a heme compound, which is an iron porphyrin compound, and this is linked with the globin, which has 4 polypeptide chains, 2 beta chains, and 2 alpha chains. And the whole thing has 4 heme molecules in it, as you can see, and those are the binding sites for oxygen. Now, there are various types of hemoglobin, and again, I'm not going into them in detail here. The most important is hemoglobin A, adult hemoglobin, which is the one that we're using right now. Another is hemoglobin F, fetal hemoglobin, which is used by newborns, or also in utero, and is gradually replaced by adult hemoglobin after a few months of birth. The important thing about fetal hemoglobin is that it has a very high oxygen affinity, which is a very good thing because the fetus lives in a very low oxygen environment. There's also a hemoglobin known as sickle cell hemoglobin that we should mention. In that particular hemoglobin, one of the chains is altered slightly because of a mutation, and it turns out that at low oxygen concentrations, the hemoglobin tends to crystallize in the cell. The cells develop all sorts of bizarre shapes, as you can see here, that they're called sickling as a result, and they also form small thrombi, and it's a very unpleasant disease as a result. Now, let's talk about the oxygen dissociation curve, which I'm sure most of you are familiar with to some extent. Here's the oxygen dissociation curve. And first of all, how would we develop an oxygen dissociation curve? Well, what we do is we would take some glass vessels, known as tonometers, put a small amount of blood in the bottom, and then above the blood we would put gases of different PO2 values. And we would then allow equilibration to take place for each of these gas experiments. We would then remove the blood, measure the oxygen concentration, subtract the amount that was dissolved, because we know what the solubility of oxygen is, and the rest of it would be oxygen combined with hemoglobin. And what we're seeing here is a nice plot of hemoglobin saturation against PO2 with oxygen concentration on this axis. Now, the hemoglobin saturation is simply the percentage of the oxygen binding sites that are bound with oxygen. The oxygen concentration, of course, is the mils of oxygen per deciliter, per 100 mils of blood. You can see on this that the amount of dissolved oxygen is very small, up to PO2s of arterial blood, about 100. If, however, as shown here, we increase the PO2 to about 600, which can occur in arterial blood when the subject is breathing 100% oxygen, then you can see that the amount of dissolved is substantially increased. But generally speaking, the dissolved oxygen is a very small fraction of the total oxygen in the blood. Now, the total amount of oxygen that the blood can carry attached to hemoglobin is known as the oxygen capacity, okay? And it's also an important term. Now, the hemoglobin oxygen dissociation curve, as we can see, has an S shape with a small curve at the bottom here and then a long curve at the top. And that the shape has to do with the change in configuration of the molecule as the oxygen is loaded. It's rather difficult to get the first molecule of oxygen onto the hemoglobin, but once the first one is on, it's easier to oxygenate, and that gives us the curve here. The shape of the oxygen dissociation curve has a number of advantages. One of them is that if we go to high altitude, and the PO2 falls substantially, say to 60 millimeters of mercury, we still have a very large amount of oxygen attached to the hemoglobin. So this flat or nearly flat upper region is very valuable from that point of view. This part, the part with the steep part of the curve, is also useful because in venous blood, when you extract oxygen, the fall in PO2 for a given amount of oxygen extracted is relatively small. So that's also advantageous. Now let's go to the next slide, which shows the anchor points of the oxygen dissociation curve. And there are three that I like to remember. They're not difficult to remember. One is that in arterial blood with a PO2 of 100, we have an oxygen concentration very nearly 100%. It's about 97%. So in arterial blood, the hemoglobin is almost fully saturated. Then we go down to what we call the mixed venous blood. That's the blood in the pulmonary artery coming into the lung. That has a PO2 of about 40 and an oxygen saturation of about 75%. And then we also, another useful anchor point is what's called the P50. The P50 is the partial pressure of oxygen for 50% saturation. And in normal arterial blood, the value is about 27. So these three anchor points are quite useful if someone says to us, well, this person's got a PO2 of 50, for example, in the arterial blood. Well, you know that it's going to be somewhere up in this range here, around about 80%, the saturation around about 80%, because we know that with a PO2 of 40, saturation is 75%, so that gives us a sort of ballpark figure if someone indicates what the PO2 is, and we wonder what the oxygen saturation is. Now, it's very important to understand how we calculate the total oxygen in blood, because we need to do that from time to time. And here we have an equation, not a difficult equation, showing us how to calculate the total oxygen concentration of blood. That's going to be the oxygen attached to hemoglobin, which is the line here, and the oxygen's dissolved. Now, how much oxygen can be combined with hemoglobin? Well, it turns out that 1 gram of hemoglobin can combine with 1.39 mils of oxygen. Incidentally, sometimes you'll see this number given as 1.36, particularly in the older literature. And the reason is that when people tried to measure it, there was always a little bit of hemoglobin that was spoiled. It was methemoglobin or something like this, and it wasn't combined with oxygen. But when we know the molecular weight of hemoglobin, as we do now, we know that the true value is 1.39 mils of oxygen per gram of hemoglobin. And then we have the hemoglobin concentration of blood, which is, ballpark figure, about 15 grams per deciliter, 15 grams per 100 mils. So in other words, the total oxygen concentration bound to hemoglobin is going to be 1.39 times, say, 15 times the oxygen saturation, which in arterial blood is, as I said, about 97%. So this would be 97% over 100, 0.97, plus the amount that's dissolved. So let's just do this calculation for arterial blood, for example, where the PO2 is, say, 100 millimeters of mercury. This would be 1.39 times 15 times 0.97 plus solubility 0.003 times 100, the PO2, and that all comes out to be about 20.5 mils per deciliter. Now, it's important to understand the relationships, to be clear about the relationships between PO2, oxygen saturation, and oxygen concentration. Because in physiology generally, and certainly in clinical medicine, it's important to understand how various abnormal conditions affect these variables. So let's look at some of them here. Let's take normal blood with a hemoglobin concentration of 15. And you can see that at a PO2 of 100, which is around about here, it has a saturation of nearly 100%, and it has an oxygen concentration of something like 20 mils per deciliter. Now, if we increase the hemoglobin concentration to 20, that's called polycythemia, happens, for example, at high altitude. Now you can see that for a normal PO2 of 100, the saturation is still 100, but the oxygen concentration is very much greater because, of course, of the increased amount of hemoglobin. By the same token, if we have anemia where the hemoglobin concentration is reduced to 10 grams per deciliter, then at a PO2 of 100, the saturation again is very nearly 100, 97%, but of course the oxygen concentration is less. Take another example. Suppose we go to high altitude and we reduce the arterial PO2 to, say, 60. Then what we'll find is that the oxygen saturation will be reduced and the oxygen concentration will be reduced together with this reduction in arterial PO2. Now, the oxygen dissociation curve is shifted under various conditions, and these are very important. Now, we talk of shifts of the oxygen dissociation curve. We could also talk of changes in the oxygen affinity of the hemoglobin. Because if we shift the curve to the left, for example, the concentration of oxygen, the saturation or the concentration for a given PO2 is increased. So that means that we've increased the oxygen affinity of the hemoglobin. And it turns out that there are 4 factors that shift the curve to the right or reduce the oxygen affinity of the hemoglobin. Those are temperature, PCO2, hydrogen ion concentration, and 2,3-diphosphoglycerate. So if we have an increase in temperature, an increase in PCO2, increase in hydrogen ion concentration, the curve shifts to the right, and the various plots are shown here. Now, you may find it difficult to remember that, but I don't, because I remember just one thing, and that is in exercising muscle, the temperature increases because of the metabolism, the PCO2 increases because the exercising muscle is producing lots of CO2, the hydrogen ion concentration increases because of the increase in PCO2 and perhaps an increase in lactate as well, and it's advantageous in exercising muscle to have a right-shifted curve where the oxygen affinity is reduced, because that means that you can unload more oxygen for a given PO2 if the curve is right-shifted. 2,3-DPG is a product of red cell metabolism, and if that is increased, the curve is shifted to the right. What happens sometimes in stored blood is that the concentration of DPG is depleted, and that means the blood has a high oxygen affinity, and that makes it difficult to unload in the periphery of the body. Okay, so those are shifts in the oxygen dissociation curve. I'm now going to move from oxygen briefly to the transport of carbon monoxide. We're not going to say a great deal about this, but it is important because, as I'm sure you know, carbon monoxide is a very toxic gas, and it's important for us to understand what's happening when CO is inhaled. And this slide will probably confuse you initially because we're showing the oxygen dissociation curve here, which we're familiar with, but we're also showing the dissociation curve for carbon monoxide. You may say, well, it doesn't look like an oxygen, it doesn't look like a dissociation curve at all. It looks like a box with a corner. Well, the fact is, dissociation curve for carbon monoxide is actually the same as oxygen. But what we've done is we've greatly compressed the x-axis so that for a very small partial pressure of CO in blood, the saturation is almost 100%. In other words, carbon monoxide has an extremely high affinity for oxygen, about 240 times the affinity of oxygen. So if you change this scale here, if you magnified it by 240, you'd get the dissociation curve of carbon monoxide. Of course, that's very important because it means that if you have a small partial pressure of carbon monoxide in the blood, it is able to tie up, to combine with a large amount of the oxygen. And that means that there's only a small amount of oxygen left over for normal metabolism. So that's a very important feature. Another important feature, which is actually one we saw on the previous slide, although I'm going to leave it here to talk about it, is the fact that if you have 1/3 of the hemoglobin bound to carbon monoxide, as is the case here, so that the available hemoglobin concentration is only 10 grams per deciliter, what's available for oxygen carriage, then it turns out that the curve is shifted to the left. In other words, the affinity of the hemoglobin for oxygen is greatly increased. And this makes it difficult to unload the oxygen in the periphery, and that's another reason why carbon monoxide is a very toxic gas. Now let's move to the transport of carbon dioxide in the blood, which is the other major gas, of course, of respiratory interest. And carbon dioxide is carried in the blood in three forms. One as dissolved, secondly as bicarbonate, and third as carbamino compounds. So let's look at these in turn. It turns out that the solubility of carbon dioxide in blood is substantially greater than that of oxygen. We saw that the solubility of oxygen was only 0.003 mils per deciliter. The solubility of carbon dioxide is about 0.067. That's about 24 times greater than the solubility in oxygen. And it turns out that as a result, the carriage of carbon dioxide in the blood, the dissolved carbon dioxide plays an important role. You can see in arterial blood here that about 5% of the carbon dioxide being carried is in the dissolved form, and that if you look at the difference between the mixed venous blood and the arterial blood, in other words, when the CO2 has been evolved into the alveolar gas, about 10% of the amount of CO2 is dissolved CO2, which has been evolved. So dissolved carbon dioxide is quite important, much more important than dissolved oxygen. Let's look at the very important subject of the formation of bicarbonate. When carbon dioxide is added to water, it forms carbonic acid. Now, under normal conditions, this is a very slow reaction. But in the red cell, there is an enzyme called carbonic anhydrase, which enormously accelerates this reaction. And this turns out to be critical in the carriage of CO2 in the blood, as we'll see shortly. The carbonic acid immediately dissociates into hydrogen ions and bicarbonate ions, and of course, this does not require an enzyme. So these are the steps required in the carriage of carbon dioxide in the form of bicarbonate. Let's turn to carbamino compounds. It turns out that carbon dioxide can link with the terminal amine group of proteins in the blood. And the most important protein by far is hemoglobin. So carbon dioxide links with hemoglobin in this way and forms what is called carbamino hemoglobin. And there are carbamino compounds with other proteins in blood as well, but they're not nearly so important. Now the next slide looks pretty daunting at first, doesn't it? But it's actually a very useful way of pulling together all the factors involved in CO2 transport in the blood. And I'm going to go through it slowly, and I think you'll see that it makes a lot of sense, even though initially it looks very complicated and daunting indeed. And what we're looking at here is the uptake of CO2 by the blood in the periphery of the body. For example, in an exercising muscle. The muscle is producing CO2 because of metabolism, and some of that CO2 then will diffuse across the capillary wall in the leg, for example, or whatever. Some of it then will be dissolved in the plasma, a relatively small amount, but some will be. But none of it in the plasma will form bicarbonate, because you need the enzyme carbonic anhydrase to do that, and the plasma does not contain any. So not very much occurs in the plasma itself. But once the CO2 diffuses into the red blood cells, shown by this great big circle here, then we can form bicarbonate and the other things as well. First of all, we should say there is, of course, some carbon dioxide that's dissolved inside the red cell, but then a substantial amount of it combines with water under the effect of the enzyme carbonic anhydrase to form carbonic acid. And this dissociates then into hydrogen ion and a bicarbonate ion. Now it turns out that these hydrogen ions are mopped up by the reduced hemoglobin in the red cell. In other words, the reduced hemoglobin is able to combine with these protons, these hydrogen ions, much more easily than the oxygenated hemoglobin. So you can see that having reduced hemoglobin in the red cell then accelerates the formation of carbonic acid. And this means that the lower the oxygen saturation of the blood, the better able it is to take up carbon dioxide. Now, the bicarbonate ion builds up inside the red cell, and therefore some of it diffuses out into the plasma. But the hydrogen ions cannot diffuse out because the membrane is relatively impermeable to them. And so in order to maintain electrical equilibrium, some chloride ions have to move back. These are also negatively charged ions have to move back into the red cell. And that's sometimes called the chloride shift, and that's necessary to maintain the equilibrium, that's part of the Gibbs-Donnan equilibrium in the red cell here. Now the oxygen, of course, is moving out, as we can see. Obviously the oxygen is moving out into the metabolizing tissue. And it turns out that these processes here increase the osmolar content of the red cell, and water tends to move in to the venous blood, but once the red cells go through the lung, the water moves out again. So let's turn to the third way in which the carbon dioxide is transported by the red cell, and that is, as we saw, by combination with hemoglobin to give carbaminohemoglobin. That is done, as I mentioned before, by a combination between the carbon dioxide and the terminal amine group of the hemoglobin. Now it turns out that the reduced form of hemoglobin, shown here, is much more able to form this carbamino compound than the oxygenated hemoglobin. So again, we have a different effect here, a different mechanism by which the reduced oxygen in the hemoglobin, the reduced deoxygenated hemoglobin, is better able to take up the carbon dioxide. So there are two effects here that make it easier for the red cell that has a reduced amount of oxygen in it to take up carbon dioxide, and this is known as the Haldane effect. Okay, so that's a summary of what happens within the red cell when the CO2 is taken up. It's a complicated picture perhaps, but if you go through it slowly as I've done, I think you'll see it makes sense, and it really puts together all the factors involved in CO2 transport by the blood. So let's just summarize the various forms of CO2 in the blood. You can see that in arterial blood, the vast majority of the bicarbonate ions of the CO2 transport is taken up as bicarbonate, carried by a carbonate. Only 5% is in the dissolved form, and only 5% is in the carbamino form. By contrast, if you look at the difference, the exchange of carbon dioxide in the lung or in the tissues, a substantial amount is taken up by carbamino and also dissolved, although still the largest amount is in the bicarbonate. Now let's look at what we call the CO2 dissociation curve. Now I should say that that's a rather loose way of talking. We use that term, of course, by analogy with the oxygen dissociation curve. Here we're looking at the relationship between carbon dioxide concentration in the blood and the CO2 partial pressure. So, that's analogous to the oxygen dissociation curve. But purists will probably say, well, you shouldn't really call it a dissociation curve, but we will, because it's the simplest way of describing it. And you can see immediately that the CO2 dissociation curve is steep and it's almost linear in the working range, quite unlike the oxygen dissociation curve, which has this marked S shape and is very nonlinear. Another thing you'll see is that the amount of CO2 that can be combined, the CO2 concentration at a given partial pressure here, is greater when you reduce the oxygen saturation of the hemoglobin. We mentioned that before when we were talking about the uptake of CO2 by the red cell, and that is the Haldane effect. So that when you've got no oxygen in the red cell, you can take up an enormous amount of hemoglobin, but even mixed venous blood with an oxygen saturation of 75% can take up more than arterial blood with an oxygen saturation of 97 or so percent. And over here we've got what you might call the physiological route from the mixed venous blood to the arterial blood. Now we haven't come across the PCO2 in mixed venous blood yet, but it's about 47 millimeters of mercury. PCO2 in arterial blood is about 40. So this is the path that's taken by the CO2 when it's evolved in the lung, and you can see the fact that the curves are different for low oxygen and high oxygen blood makes this path even steeper. Let's have a last look at the oxygen and CO2 dissociation curves. We've got them both on the same axes here. And immediately you can see that the CO2 dissociation curve is much more linear and it's much steeper than the oxygen dissociation curve. And one of the results of that is that the difference in partial pressure between the arterial and the mixed venous blood is very much less for CO2 than it is for oxygen. In oxygen, you've got an arterial PO2 of about 100, mixed venous PO2 of about 40. By contrast, for CO2, the arterial PCO2 is about 40, and the mixed venous PCO2 is about 47. So there's a very small arterial venous difference for PCO2. In spite of that, of course, the amounts of oxygen and CO2 that are being exchanged in the lung or in the periphery are about the same. And we'll be talking about that much more in a short period of time. But although the arterial venous difference for concentration of oxygen or CO2, almost the same, the PCO2 difference are very striking. So let's just summarize some of the main points we've made. First of all, we pointed out that the importance of understanding the definitions of concentrations of gases and their partial pressures. Partial pressure of a gas is the fractional concentration times the barometric pressure. We then looked at the important effect of water vapor on partial pressure and showed that in moist inspired gas, the partial pressure of water, the water vapor partial pressure is about 47, and so that's got to be subtracted from the total barometric pressure in order to get the partial pressure of a gas in the moist inspired gas. We then looked at the very important topic of the partial pressures of a gas in a liquid, and we pointed out that the only sensible way of thinking about them is that the partial pressure of a gas in a liquid is the partial pressure of a gas in equilibrium with the liquid. We then looked at the carriage of oxygen by the blood. We pointed out that the oxygen in solution is nowhere near sufficient to look after the metabolic requirements, particularly during exercise, and therefore we have hemoglobin. We mentioned that the heme is an iron porphyry compound and that we have 4 polypeptide chains in the globin protein, 2 of them alpha and 2 of them beta. We talked about the way of deriving the oxygen dissociation curve, the advantages of its S shape, in particular that if you go to high altitude and your alveolar PO2 falls a little bit, then you lose very little oxygen in the blood. Another advantage in the periphery is that the dissociation curve is steep so that you can withdraw a lot of oxygen from the blood with a relatively small change in partial pressure. We referred briefly to the hemoglobins, the fetal hemoglobin and sickle cell hemoglobin, the latter being, of course, an abnormal one responsible for sickle cell disease. We briefly mentioned the importance of understanding the differences between the PO2, the oxygen saturation, and the oxygen concentration, because these vary in ways that initially may be confusing, but if you think it through, they're not all that difficult. We mentioned the factors affecting oxygen affinity, and we pointed out that reducing the CO2 increases the oxygen affinity, and I forgot to mention that this is known as the Bohr effect. Christian Bohr was a famous physiologist, and he was the person who has his name attached to this very important effect of CO2 in blood affecting the oxygen affinity. We then talked very briefly about the carriage of carbon monoxide in the blood, of course not a respiratory gas, a toxic gas, and pointed out that it has a very, very high affinity, 240 times the affinity of oxygen, and so it's a dangerous gas because it combines with a lot of the hemoglobin and doesn't leave it available for oxygen carriage, and it also incidentally shifts the oxygen dissociation curve to the left and makes it more difficult to unload oxygen in the periphery. We then turned to carbon dioxide transport and pointed out that this occurs in 3 forms: dissolved, as bicarbonate, and as carbamino compounds. We went into some detail in the way carbon dioxide is taken up by the blood in the periphery and pointed out that the lower the oxygen saturation, the more CO2 can be taken up, known as the Haldane effect. We also looked at the CO2 dissociation curve, showed that it's much steeper than that for oxygen, and it's also much more linear, and finally pointed out that this is the reason why, although the difference in CO2 and oxygen concentrations across the lung are very similar, the PCO2 difference is very much less than the PO2 difference. So that's the end of this brief discussion of the transport of oxygen and carbon dioxide by the blood, and we're going to go on next time to look at the acid-base effects of the CO2 in the blood. I'll see you then. Fully compensated one here. Now we have a name for the distance between the point, the vertical distance between the point and the normal buffer line. And that is called the base excess. It's a measure, you see, of the amount of bicarbonate which has been added. And the base excess, in this case, the example I'm showing here, This is about 24, this is about 48, so what's that? Something like 24, if I've got my sums right, would be the base excess in milliequivalents per litre, something like 24. Okay. Okay, so that's respiratory acidosis. Let's go on now to respiratory alkalosis. And perhaps before I do that, let's just mention what are the causes of respiratory acidosis. Well, I mentioned alveolar hypoventilation, and that can be caused, for example, by an overdose of certain drugs, cause hypoventilation. Morphine derivatives, for example, can do that. That would be one example. Another cause, though, of an increased PCO2, you recall, is ventilation.